One, and welcome to our lecture, Math 167 for September 18th. And recall from last lecture that in chapter 3 we introduced our second function called the quadratic function, and it's any function that can be written in this form. One condition though is a cannot be equal to 0. If it is, you don't have a quadratic function. Also, we could write our quadratic function in this vertex form. And if it's in this form here, we can immediately write down what the vertex is for the quadratic function. I'd like to begin with this example. Given for some quadratic function that the vertex is at, let's put the vertex at 2, 3, and it contains the point, well, contains the origin. So the function goes through the origin. So what we want to do is, hey, suppose I have a quadratic function where the vertex is at 2, 3, it passes through the origin, find the function. You're going to say, okay, that will be f of x is a times x minus 2 squared plus 3. Okay, so we have that much. So there we've used the fact that the vertex is at 2, 3 to write this. But now we got to figure out what a is. And we can do that using this information here. We know that our output y is equal to 0 when x is 0. Okay, so you just choose A so it fits. Now, the right-hand side is equal to 4a plus 3. That gives us 0. So it looks like a is equal to minus 3 over 4. And we have our final answer, f of x is equal to minus 3/4 times x minus 2 squared plus 3. And hey, what we'll do is we'll graph that using Desmos and see how we did. So going over here for a moment to Desmos, and hopefully you can see that. Turn this one off. Minus 3/4, there's the quadratic function, and let's see. Yes, the vertex is at 2, 3, and it goes through the origin. All right. Now, another problem before we move on to the next topic is we're going to do an optimization problem. We did one last class, finding a point on a line closest to another point. For this particular problem, I want to do the following. Here, we're going to say, suppose the demand equation for a product is given by. So the demand equation for some product is a function of the price, what you sell the product for. And it's going to be equal to, for this particular product, it's determined to be minus 5 times the price plus 100. Okay. So we have this demand equation for some product. Here it is. So this tells you, so this is like, hey, if x is the number of items that are demanded, x is equal to minus 5 times the price plus 100. That is a linear equation, a linear model. And it is decreasing. We would expect it to be decreasing because as the price increases, the demand will decrease. Okay, well, what do we want to do? We want to find the price, that maximizes revenue. Okay, so what should I sell this product for if I want to get the maximum revenue? Change our page here. Well, the revenue, how much money you bring in, we'll use the letter R for revenue. The revenue actually depends on how much you sell it for. The revenue is going to be equal to how many you sell times what price you sell each item for. There's your revenue. But how many are we going to sell? That's given by our demand equation. So my revenue is going to be equal to the demand equation, which was minus 5p plus 100 times p. And what we need to do is maximize this. You say, what do you mean maximize? Find the maximum value. Well, no, hey, we're not asking you to find what the maximum revenue is. We're asking you to maximize, find the input that makes it maximum. Find the optimum price. Maximize this. Well, it turns out that since it's going to be a quadratic function, let's see what it's equal to. It's minus 5p squared plus 100p. That's quadratic, and we know the maximum occurs at the vertex. See, this is concave down. So when you plot it, it's going to look something like this, and there is some optimum price. And how do we find that? Well, the x component of the vertex is given by the opposite of b over 2a. So that's going to be equal to, hey, this is ax squared plus bx plus, for this problem, c is 0. So the opposite of b is minus 100 over 2 times minus 5. That's equal to 100 over 10, $10. $10. So for these type of problems, now you got to be a little careful because some of the problems in my math lab, they're already giving you the revenue function, and they're just saying maximize the revenue function. They're giving you this. What we're doing here is we gave you the demand function, x, and you had to generate the revenue function and then maximize it. So hopefully next Tuesday you won't have trouble doing a problem like that on your exam. Well, we have this final topic to look at, and that is inequalities. Now, linear inequalities, that topic is found in the appendix in the textbook. I believe it's Appendix A9. So you will read about that in the appendix. So what is an inequality? Well, inequality are these symbols. It's not it's like less than or equal to, greater than equal to. Hey, that's it. Those are your inequality symbols. And if you have an expression like 2 times x plus 3 less than or equal to 5, it's It's not an equation. That's called an inequality. So linear inequalities are solved very similarly to solving linear equations, with a few exceptions. Okay, so here, if I want to solve for x here, what I need to do is isolate x on one side. Hey, if it's true that 2 times some number plus 3 is less than or equal to 5, what numbers satisfy this? Now, the thing about solving linear equalities is your answer is a set. Your answer is a set. So we isolate x on one side. How do we do that? By using similar maneuvers we use when solving a linear equation. We move the 3 over, so we can subtract 3 from both sides. That's fine. 2x is less than or equal to 5 minus 3, which is 2. And you can divide both sides by 2. So x is going to be, as long as x is less than or equal to 1, 2 times x plus 3 is going to be less than or equal to 5. Now, we like to write the answer in interval notation. So x less than or equal to 1 means from minus infinity up to 1, that's less than or equal to, there's your answer. It's a set. Now, sometimes, just to check it, it's not an exhaustive test, but it might pick up a quick little error if you did something, say, hey, let me choose some number in here and see if it works. Just let me pick some number in this set, plug it in here and see if it works. I'm going to choose x. Okay, so does x equals 0? Excuse me. I'm going to choose x equals 0, put it up here, and see if that works. Is it true that 2 times 0 plus 3, is that less than or equal to 5? Let's see. 3. Is 3 less than or equal to 5? Is it to the left? Yes. That works. So solving linear inequalities is like solving a linear equation, but there's one exception. And that is when you multiply both sides by a negative number. Watch this. Suppose x is greater than 2. Now, to visualize that, draw a number line. Here's 2. Here's the origin. If x is greater than 2, it's over here. X greater than 2. And someone might say, well, what can you tell me about the opposite of x? If x is greater than 2, let's see, if we come down here, see, the opposite of these numbers are over here. The opposite of 3 is minus 3. Okay, so this set, the opposite of this set is this set. If x is greater than 2, that means the opposite of x is to the left of negative 2. Now this is true. If this is true, this is true. But notice this. Suppose someone tried to take this and say, oh, to figure out what the opposite of x is, I'm going to multiply both sides by negative 1. So they do this. Minus on this side. That does not work. That is wrong. The opposite of x is now greater than negative 2. That is wrong. Oh, so what do? When solving inequalities and you have to multiply or divide by a negative number, you flip this symbol. You have to flip this symbol right here. Okay? So if you have x, suppose I got this as a different problem. I got the opposite of x is less than 3, and I want to solve for x. You multiply both sides by negative 1, And that's going to say x, and you're going to get minus 3 here. But when you do that, you got to flip this. Okay. Now, one more issue with inequalities is suppose your inequality contains an absolute value symbol. Absolute value of x, say it's less than 2. Solve it. And you say, well, isn't it already solved? It's telling you the absolute value. No, I want to know what x is. If the absolute value of x is less than 2, what is x? And, well, notice what this is saying. Here's the origin. Over here is 2. And over here is minus 2. So hey, this is saying your distance to the origin is less than 2 units. If that's true, where are you at? You're anywhere in this interval. So to remove the absolute value, if the absolute value of x is less than 2, that means x is less than 2. Yep, but greater than minus 2. Okay? So, yep, if x is less than 2 units from the origin, where can you be? Here. And interval notation, minus 2, comma 2 for that answer. Now, another example is absolute value of x minus 2 is less than 5. And we want to solve that. How do you remove this absolute value? The way you do it is we're saying the absolute value of something is less than 5. You know, something in there. So it means that something, that x minus 2, let me put in parentheses. Now whatever is in here, that means it lies between 5 and above minus 5. That's the first step you got to do to remove those vertical bars. See, now hey, notice, hey, what is this thing called? You know, what is this? This is a compound. This is still an inequality. You got two of them. It's called a compound inequality. Compound inequality. So what we want to do is I need to know what x is. So I can add 2 to everything. So x is going to be less than 7 and greater than minus 3. So let me kind of visualize this for a moment. Okay. So here, let's say here's the origin. 1, 2, 3, minus 3. 1, 2, 3, 4, 5, 6, 7. Here's 7. And where was that 2? That 2 is right here. Okay, let's write the answer down, but then let's interpret what this answer means. So the answer is that you are lying between minus 3 and 7. See, what this is saying here is the absolute value of this is actually the distance between two numbers. The absolute value of a minus b is the distance between those two numbers. Let me show you. Suppose one number is equal to 2 and the other number is 4. You know the distance between those two numbers is 2, but let's see. That's equal to absolute value of minus 2, which is 2. So this is saying, hey, I want all numbers, I want the distance between x, some number, and 2 to be less than 5. So I want the distance between these two numbers to be less than 5. So what's the possibility? Let's see. 2. All the numbers that are less than 5 units from 2. Here you go. 2 up to 7, 2 to minus 3. That's your answer. Now, a few more things with linear inequalities. You could have absolute value of x greater than something. the distance to the origin is greater than 3. So let's look. All right. Here's the origin. Here's 1, 2, 3. 1, 2, minus 3. If the absolute value of x is greater than 3, that means you are either over here, you're more than 3 units from home, which is the origin. So you're either here or here. So notice how we have to write the solution here. This means that x is between 3, let me do this one here. Minus infinity up to minus 3. But you could also be here. So we're going to take the union of those two sets. 3 to infinity. Thus, if you have the absolute value of x greater than something, when you remove the absolute value, sometimes you got to draw a little picture. It means this happens. So if I say the absolute value of x minus 2 is greater than 1, that means this thing inside here, if it's greater than 1, this thing inside here is either less than, okay, now I wrote this down here, but I should have wrote this here. If absolute value, let me go back over. Absolute value of x is greater than 3, that means x is to the left of negative 3, or x is to the right of 3. Then we put it in interval notation. Here, if it's greater than 1, that means you're less than negative 1, or try that again, x minus 2 is less than negative 1, or this thing inside here is to the right of 1, x minus 2 greater than 1. Then you could look at this, that says, hey, x is less than minus 1 plus 2, which is going to be 1, or x is greater than 3. So to write this as the solution, it's going to be minus infinity up to 1 union 3 up to infinity. And now let's interpret this result. See, what we're here saying is the distance between two numbers is greater than 1. Hey, I want to find all numbers that are more than 1 unit from 2. Okay? And let's look at this. All numbers that are more than 1 unit from 2. Here's 2. Here's 1. Here's 0. Here's 3. If you're more than 1 unit up, went off the screen, let's fix it. If you're more than 1 unit from 2, more than 1 unit, you are over here. You are greater than 3. Here we go. Or you're to the left of 1. There you go. That's it. Now, one last thing with inequalities. Here. So everybody seems like usually say, okay, I understand. Multiply both sides by -1, you have to switch it. But notice this. Suppose I say 1 over x greater than 1. We ask you to solve that. So this is what the students would usually try to do. They're going to go over and say, I need to clear the fraction. I need to know what x is. So I know what I'm going to do. Which, if it was an equation, this would be okay. So I'm going to multiply both sides by x. So I get 1. And so what I'm saying, 1 over x greater than 1, that means x is less than 1. But let's go to Desmos and look at and see that this is wrong. And then we'll tell you why it's wrong. Okay? So go to Desmos. Here we are. And we want to look at y equal to 1 over x. And I'm going to plot y is equal to 1. And I want to know when is 1 over x greater than 1? Okay. And that only happens, hey, when is the green above the purple? Only between 0 and 1. It's not greater over here. So it's not x less than 1. See? 1 over x. When is it above the purple? Just for x values between here and here. But we go back and look at this. We said it's true for all values of x less than 1. That's the wrong answer. And so the question is, well, what did we do wrong? Why did we get the wrong answer? Because when you multiply both sides by x, you don't know if x is positive or x is negative. So because if x is negative, then you're supposed to reverse this. So you can't do that. You can't multiply both sides by x. So the question is, well, then how do I solve this? How do I solve 1 over x greater than 1? The answer is, that is not a linear inequality. This is not linear. Not linear. That's not a linear equation. So this is another type of inequality that we covered later. All right, it's called a rational function. So how do you solve it? That's chapter 4. Hold off on that chapter 4. Now, however, there's certain cases that you can solve. If you have something, like if you have 3 over x greater than 0, that's not linear, just like for the same reasons we said here. But we can solve this one. You might see this one in my math lab. Because what we're saying is, this number is positive. We're saying this number is positive. Hey, if this is positive, that means the denominator has to be positive. A positive divided by a positive is positive. So the solution to this is x greater than 0. Okay, well, we're going to do this lecture in 2 parts. That is the conclusion of part 1. So there'll be 2 separate videos. That's the conclusion of part 1, where we reviewed a little bit of quadratic functions and we did linear inequalities. Part 2, we will do quadratic inequalities. Okay, so we'll stop here.